Very good afternoon. This is Sumohana here. The folks on the call, can you hear me?
Yes, Professor, we can hear you.
Yes, sir.
Okay, great. Yeah, I'm sorry about the delay. There was some issue with the links. But yeah, hopefully we shouldn't affect the material that we cover. I'll start to share my screen. And once again, I request one of you to please confirm if you can see my screen. All right. So we will be looking at the topic of neural networks today. And I think these slides have already been communicated to all of you. So we will look at neural networks in this session today in the context of supervised learning. You can study neural networks in the context of unsupervised learning as well. But for today, we will be focused primarily on the supervised learning setup. Okay, so I would like for this session to be as interactive as possible. And for all the participants, I would encourage you to have a pen and paper in handy, because we will work out a few things on pen and paper. I'll, of course, write on my screen, so you can all see it also at your end. But I do encourage all of you to do this with a pen and paper at your end as well. Okay, and please feel free to stop me at any time if you have any questions. And I do hope that at the end of this session, you will be able to appreciate why these neural networks have become, pretty much the cornerstone of modern machine learning. So that would be the goal. And of course, we will also understand how we can end up training a neural network model. So that is going to be the overarching goal and theme for our discussion today. So on the opening slide itself that we have here, I have on the left-hand side, a neuron that we would find in a human. And on the right side, we have a visualization or an abstraction of an artificial neuron. And why do I have this comparison here? Well, just to give you a little bit of a historical perspective on why we are talking about neural networks in the first place. Well, the motivation for people to study these artificial neural networks comes from the behavior of neurons that we find in our own nervous system. And the nervous system that we all have is, and especially the neurons that we find in our brain, are perhaps one of the, the most interesting physiological phenomena that one could study, and that has essentially endowed us with the intelligence that we all possess. And historically, people have been trying to not only understand the physiological properties of a neuron, but also try to mimic its behavior with the bigger goal of trying to see if we can understand how the brain itself works, and if it's working can be replicated artificially. So that is the broad connection between artificial neurons and the neurons that we all have in our brains. But the similarities between an artificial neuron and a real neuron pretty much are only at the conceptual level, meaning, or at this high level, a comparison only, because the inner workings of a neuron and an artificial neuron are completely different. But one fundamental commonality between the neuron, that is the physiological neuron, and the artificial neuron, is the fact that both of these are nonlinear systems. And it is this nonlinearity that gives it the strength that other linear models do not possess. And it is this nonlinearity also that has led to the success of these neural networks, especially deep neural networks. And to give you a loose analogy again of this nonlinearity, so typically how a physiological neuron works is that it is connected to other neurons, and when the input that it receives from the other neurons exceeds a certain threshold, it quote unquote fires. And this firing mechanism or spiking mechanism, as people call it, is very, very non-linear in nature. And once this threshold potential is crossed, then the neuron fires, and this is how information is communicated. This is how information is also, it's also how neurons learn to train themselves and so on. Now, this nonlinearity is what we will also see very shortly in our artificial neuron. And in our case, in the artificial neural network setting, the goal for this firing or this nonlinearity is to be able to make categorical predictions. Again, we'll look at all of these concepts in further detail very, very shortly. So again, very loose connections between a physiological neuron and an artificial neuron. And it was called a neuron, an artificial neuron in the first place, because it was trying to mimic what we all do in our brains. So that is why I felt it's just worth a few minutes of our time to have this very high level comparison. Of course, people have done a lot of study in trying to see if these properties can somehow be modeled and can be used to solve problems related to learning. But we will leave our discussion about this comparison at this point, and we will move forward. So what we will first do is we will first have a very quick recap of what you have all been learning so far in the program. So moving forward, like I said, in this discussion, we'll be focused on the supervised learning branch of machine learning itself. So before we go ahead, by way of a recap, I'll just pause here and try to see what your understanding of machine learning itself is. So if someone were to come and ask you, hey, you're looking at this AIT program and you're talking about machine learning and AI and so on. So if you were to describe to a lay person what machine learning is, how would you do it? How would you describe what machine learning is? You can use your microphone or you can use the chat box. And I request the moderator to please read out the chat box because I'm only logged in from one device if there are answers in the chat box. So what is machine learning?
Like the system is trained on some data, so it will predict some output.
Okay, fine. So, and what do you understand by a machine itself? So if I understood, if I heard the response, so we have a machine and then we're trying to train it from data points. That's absolutely right. But my question is, what is a machine?
The device which is making our work easier in the specific fields.
Computer program.
Okay.
Which can learn and adapt new things.
Okay, very good. So if you think about what you've been, learning so far, a machine is nothing but at the end of the day, a function, right? So if it be it supervised learning or unsupervised learning, what we are trying to do is that we are trying to make sense of data that is given to us, right? And this could either be, in the supervised setting or in the unsupervised setting. And we of course have, reinforcement learning as well, but we will not, touch upon reinforcement learning in this discussion at least. So at the end of the day, a machine is nothing but a function, right? So you're given a set of data points, and you want to see if there are, say, trends in the data. Say you want to learn if you can cluster your data, right? And how do we do this clustering? So we say that you initialize the number of clusters, and then you see how many points there are that are closer to one cluster center than another, and so on, right? So there you're trying to make sense of the data. And we are all doing this using functions, right? Now, another example could be, say that I am given a set of data points, and say that I want to fit a line, for example, to this set of data points, right? So when I say that I want to fit a line to this set of data points, what do I need to do? At a high level, you don't have to give me the exact expressions or equations or any such. So when I say that I want to fit a line to a set of data points that are given to me, so we have, and let's say that we just operate in the XY plane, okay? A simple 2D plane that we have, right? Maybe I'll just write it out. Right, so here I have a bunch of data points, right? And then my goal is to be able to, we'll just use this mode. Yeah, better. Okay, and say that I want to fit a line to these data points, right? And this is X, this is Y, and say that this is X1, Y1, X2, Y2, and so on. Say that I have N such data points, okay? And so this is also a very simple example of a machine learning problem, right? So I want to fit this line to this set of data points, correct? So what I want to do here is to find some f of x, okay, and it has some parameters, and this is going to accept an x, and let's say that I have this form of the line. So again, you know that there are different ways in which I can write the equation of a line, correct? So when I say that I want to learn this model, what are we doing? I've given you data points also, right? So this is our data set. So if you want to call this is the set of data points that we have. And what I have here is actually my machine or my model, right? And when I say that I want to learn this model or learn this machine, what is our goal now?
We learn the parameter theta.
Okay. And in this specific case that I'm looking at, what are the parameters of this particular model that we have?
There's C and M.
C and M, slope and intercept.
Exactly. So very good. So, and how do we end up learning the model parameters M and C?
We first initialize the epoch value, like number of iterations, and according to the obtained equations of those parameters, like when we normalize the equation, we get those parameter
Okay,
equations.
yeah, I think we'll keep it simple since our discussion is still only beginning. We'll keep our discussion at a fairly low level, and let's say maybe at our 10th standard or 11th standard type of level. So you're saying what I'm not saying that what you're
We
saying is
initialize the
wrong.
data points and we compute the equation.
Okay, so when we say supervised learning, right? So let's say that we want to find or solve this in the supervised learning setting. So you're all absolutely right when you say that you want to find M and C. Perfect. But my question is how? How do we find M and C?
Using ordinary least square method or gradient descent.
Sorry, can you? Sorry, your voice was a little muffled. Can you please repeat?
Sir, using ordinary least square method or gradient descent method.
Okay, so that is the method that you want to use. But the question is, before I apply that method, there should be some goal for us, right? What should be our goal?
Sir, we need to find a function such that it passes through the maximum data points.
Very good. And so what? So how can we express that so that we can then try to find our M and C using the techniques that you have been talking about?
Yes, sir. Then we can minimize that function so that we get the optimal values for these two parameters.
Very good. So can you give me an example then for how we can measure how good our model is?
Sir, we can calculate the least squares method we can use to calculate the
Okay.
error between the predicted data point and the actual data point, and then we can minimize it.
Okay. And so what do you mean by least squares or squared error? So if I understand what you're saying that let us set up the problem so that we want to minimize the squared error between the model's prediction and the ground truth, right? Is that what you mean?
Yes, sir.
Okay, so that is what I was hoping to hear from all of you. So what do we mean by supervision? That's why I was asking you this question. So what do we mean by supervision?
So we are aware of the class labels, or the model is working under some supervision.
Very good. So essentially, the set of the data points that I have chosen here. So this is essentially my input to the model, and this is essentially the label that I assign to every data point that I have. Okay, so why are we talking about this? So if you just rewind just a minute, then you correctly again said that we need to be able to minimize the squared error, right? Or the difference between the model prediction and the ground truth, right? So in supervised learning, the key characteristic of a supervised learning setup is that we have, quote unquote, the ground truth label that is available for each of the data samples or data points that are available in the data set. So we always have a tuple. So we have a data point X and a corresponding label Y. And the whole goal of supervised learning is to be able to find a function F that does what?
It maps the input X to Y.
Exactly. So this is a function that is parameterized. So that's why we've written, if you see here, we've said we have a model which is fx theta. Okay. And the job of this function is to be able to map the input to its ground truth label. And it should do this so that a certain requirement on the model is satisfied, right? Meaning, again, like all of you were saying, it should be able to say minimize the squared error in this case. Okay, so that is essentially the goal. One of the, it's a part of the goal of supervised learning. Okay, and we will end up during the training process, we will end up finding, again, like you were all correctly saying, the model parameters M and C in this case, so that such that some loss function is minimized or optimized. Okay, and the moment we say loss, we need to have loss with respect to what is golden or what is the ground truth, right? So essentially, what we will end up saying is that this fx theta in this case is essentially going to be labeled as y hat, and that is what we will be using as the prediction. That's what we'll be using to denote the prediction of the model to the input. Okay, so in the case of neural networks as well, we are essentially going to be doing the same thing, just that we are now going to introduce a nonlinearity in our model. Okay, and say that we have now a loss function. So let's say that we have, you can either call it L of theta, and this loss function is going to go over say we have n training points in our data set, right? So we want to minimize this loss. So here we are choosing a specific loss. So this could also be abstracted to something like this, some distance that I can. So in this case, I'm using the squared error as the distance, right? And through our training process, what we want to do is, can we find this? So we set this to 0 and find the model parameters that are going to minimize this loss. Okay. And one other important point about supervised learning is that, and even in the case of unsupervised learning for that matter, the model parameters that we end up finding through this training process, as we call it, is clearly going to be a function of the training data set. Okay. Now, again, you've seen all this. This is just a quick recap. Are we done in the supervised learning setting? Is this all that we want to do? Do we simply want to find the model parameters, which in this case is M and theta? And is that all?
So now we want to see how our model generalizes on future data points.
Excellent. So that is also central to all supervised learning problems. At the end of the day, the goodness of a model is determined by how well the model is able to generalize on previously unseen input data points. Okay, so this is again something that you should all always keep in mind, that the goal of supervised learning is not just to find the optimal model parameters on the training set, but we also want to check how well these model parameters are able to behave or perform on previously unseen data points. Okay, and if you see that you have issues during testing, right? Suppose that your training went very well, you're able to achieve very low error, training error that is, but then you end up making much higher error on the test data points, you know that there is an issue. We won't get into those details now, but just for completeness, we'll just mention that here. So this is essentially what we will be doing for a specific model in our discussion, and that model happens to be a neural network. Okay, so I hope the recap is now pretty clear. So in the case of supervised learning, so we have a set of data points which are tuples. Right, and then we also have essentially a model. So our y hat is going to be defined in this fashion. And we also have a loss function, which is going to be defined over the set of training points that we have. If you wish to be precise, what we can do is, let me call this maybe xt, yt, and say, let's say xn, yn. So up until this point, we'll use for training, and the remaining data points we'll use for validation or testing. Okay, and again, I'll be precise here. So we'll say that we are using the losses evaluated over the training set. Then you find theta star, which is our min L of theta. Now, ultimately, we also want to check, evaluate model on validation set. So going back to the earlier question, this is my machine or model. Okay, so this is a very quick recap of supervised learning itself. Okay, now there are different problems that we encounter in our day-to-day lives, be it trying to predict what tomorrow's weather is based on today's weather, or be it predicting stocks, or predicting what the next word would be when you are typing out a sentence, and so on and so forth, right? So in several of these scenarios, in some of these scenarios, I should say, there is perhaps a simple input-output relationship, okay? And in some situations, the input-output relationship may not be that obvious, okay? So this also brings us to the question of model selection. Again, I'm only mentioning that at a high level here. We won't get into that here, but model selection is a very important activity also when you want to try to find what model is best for a given problem, okay? And to motivate neural networks, I have an illustration that should convey to you a very common, machine learning example that you probably have come across in several places. The simplest of these is, where you have images, say, of cats and dogs and birds and fish and so on, and we want to be able to find an input-output relationship here. Okay, so how do we solve such a problem? It's clearly not obvious, right? That it's not a problem like what we just saw a minute ago, like where I know that my input-output relationship can be captured nicely using this line that we have here, right? So I drew this line here, and I could simply see from the visualization that a line is, going to suit the problem at hand. But now we have something that's not so trivial or so obvious, right? So again, we have tuples. So we have images now of cats and dogs and these other classes, and we have the corresponding labels. So it's still very much in the supervised learning framework that we have established or reviewed, right? But now the question is, how do we come up with a mapping between my input and my output? Okay, do we even know if there is a simple linear relationship? First of all, the question also is, how do we even represent our images as in a manner that a machine can accept it and then try to apply some operations for us to then be able to map it to the output label. So before we go ahead, I would again like to pause here and see what your thoughts are on how maybe we could solve a problem like this.
Hello.
Yes, please go ahead.
Yeah, sir. We convert this image into a matrix according to the density.
Okay, very good.
We convert every image first. We train it according to the model.
Okay, so what you're saying is that we simply use
computer vision.
Right. So if I understand what you're saying, we use the digital representation of the images as the input, and then we use that as our X. So the representation X is nothing but the pixel intensities that we have for each of the images that are present here. And then we try to find an appropriate function that is able to map it to our output. Okay, so let me just write out what you're saying. And I'd like to invite more inputs as well. So here, so what we are saying is that, so let's use, say, a vector representation or a tensor representation. Say that we have, just for simplicity, say that we have 32 cross 32 images, and we have 3 of these images, 3 of these channels corresponding to R, G, and D. And now what you're suggesting is that our y hat is going to be this f, x, and theta.
Yes, sir.
Okay, fine, perfect. I think this is perfectly fine. And then that is the first step. So what is the next step then?
Like individually we train cat, bird, dog, fish according to their categories as classes.
Okay.
And now we give this cat image as the testing validation set.
Fine.
And we
fine. Okay.
obtain the y hat.
Fine. So the process is perfect. What you said is perfect. But the question I have for you is, what is this?
Cost function.
No, what is the machine that we want to learn? So do we still want to learn a machine that is linear? Like, do I simply say that I have,
no, it's
if I were to write this?
It's non-linear data.
Okay, so we let's write out some simple example. Now, suppose that I have a function, say like that, or maybe I will just write it
We
like
can
this.
use KNN and classify for such problem.
Okay, let's go slowly. Say that I have this as my y hat. Okay, and then maybe I say that. Something like that. Just to, again, just only to map it to what we had seen here, right? So now the M is becoming our, say, W here. Okay, and then we want to, so these are all the parameters of our model. And then we follow the exact same procedure that we had done previously. Okay, so this is just one example. I'm not saying this is the way we have to do it, but this is one simple way in which we could potentially try to solve the problem at hand. Okay, but the issue here is that we really, first of all, when I was operating in this, in the previous example that I gave you, it's very easy for us to visualize the input-output relationship, right? I just had a one-dimensional input and I had a corresponding label. So I can just throw these points on this XY plane and try to understand what the input output relationship may be. Okay, in this case, I've just given a simple linear example, but it could be something else also. It could be a curve that looks like maybe y equal to x square or such. But the bigger point is that I can visualize. Okay, so I can essentially look at how the points are distributed in this xy plane, and then again bring in our intuition to solve this problem, right? But now, if you see, in the current problem that we have, the input dimension that I have is 32 cross 32, which is 1024 times 3. So that's roughly, 3000 and odd dimensions, right? So if I were to try to do this visualization again in this large dimensional space, it's very difficult for us to see what is going on in this high dimensional space. That is one issue, right? And so I will no longer be able to use our intuition to solve such a problem. That's one of the issues. And secondly, and importantly also, is if I can't do this visualization, and if I were to simply use, say, a linear model, then it may not be sufficient to be able to learn the input-output relationship. And these are a couple of motivating points for us to see if we can do better, or if we can come up with a set of flexible models that will allow us to capture simple input-output relationships, like say lines, as well as input-output relationships that are very, very complicated or complex, I should say, which is non-obvious even if we were to visualize. Okay, so this observation is what led to people trying to come up with a generalizable class of these models or functions, and that they came about by applying a very simple operation to over and above the linear operation, and that is nothing but applying a non-linearity. So now we say that we have y hat, which is again this fx theta. Now here, this will end up being a composition of a linear operation and a non-linear operation. So I'll write it like this: a non-linear operation and a linear operation. Okay, and so this we can simply write. This is typically symbolized using the sigma operation, and the linear operation we can say write it as something like this, like whatever we had written earlier. And so this has a lot of power embedded in it, and how that is we will see also in a minute. Okay, and when we take further cascades or compositions of this fundamental linear non-linear composition, that is what is going to lead us to a class of functions that are extremely powerful, and that is the reason behind the success of these neural networks. Okay, we'll go slowly. First of all, we'll even try to express this pictorially, and then see what happens when we have a cascade of these functions. Okay, so just to recap our motivation to study neural networks. Firstly, our input could be high dimensional, which makes visualization very difficult. And secondly, it is not always the case that we have a simple input-output relationship among our data points and the corresponding labels. Okay. In such a case, we will need to come up with a class of functions that are able to capture this nonlinearity nicely and compactly. And that is what leads us to our neural network. Okay. So I'll pause here and see if you have any questions or any comments on what we have said so far. And the illustration that I have here is just to give you this demonstration that many times the input-output relationship is absolutely not obvious. Okay. To reiterate that point, how do I take, say, the image of this cat and map it to, say, the same number 1? Now, suppose that you want to do, like you were saying, categorical, labeling. Say I give it these labels, right? So how do I take this set of pixels that I have here and map it to the number 0? And how do I take the set of pixels here and map it to the number 3? Clearly not obvious, right? Yeah, so I'll pause here and see if you're able to appreciate the difficulty of a general, machine learning, supervised learning problem, and how simpler models like linear models may not be sufficient to tackle what we have at hand. Any questions or comments? Please feel free. So just to reiterate, just compare the problem here.
Sir, hello.
Yep.
So if it is a high dimensional data, can't we use dimensionality reduction?
Yeah, sure. I mean, that's definitely possible. But the bigger point that I'm trying to make here is about the non-obvious nature of the input-output relation. Yes, you can certainly apply, PCA or any other techniques to reduce dimensionality. But the question is, will it also guarantee linearity in the input-output relationship? We don't know. It's not obvious again.
Yes, sir.
Okay, are you all with me so far as to why we may need, a more powerful class of functions?
Yes, sir. Yes, sir. Got it.
Okay, yeah.
Because there may be a cat and a dog at exactly same grid lines, but if the densities of a cat image of the cat and image of the dog are same, then there may be a misclassification.
Yes, most certainly. So again, that's the whole point. So what would be, a way to draw these boundaries between these classes of inputs, right? So that is not obvious, at least not to me in the way we have written things out here. And at the end of the day, many of the simpler classes that you have seen. So before we go further ahead, can you please tell me what are the different supervised learning models you have studied so far in this lecture series?
Linear regression,
Okay.
Lasso and Red's regression,
Okay.
logistic
Fine.
regression,
Okay.
and
Okay.
support vector machines,
Okay.
chain and decision trees.
All right. So in many of these cases, like say suppose let's look at the SVM, right? So in the SVM also, what do we end up trying to do? So we have, say, again, classes of points, like we have points in some high dimensional space, and we are trying to end up we want to find the optimal separating hyperplane, right? As an example. So how do I find this plane so that this is as far away as possible from both of the classes that I have, right? And then you formulate the problem and you're able to solve it in a certain fashion. Now, again, here, can we find a simple, linear separation between these classes, right? And it's not obvious that we can always do it. Of course, there are ways even in the SVM framework where you apply a kernel, for example,
Yes, sir.
to
RBF,
map
we apply
your
RBF
point.
pattern.
Yeah, so you can apply, an RBF kernel or other types of kernels to map your low dimensional data to a higher dimension, and then try to see if you can find this separating hyperplane, right? But again, the question is, do we do this by trial and error? How do I know whether a particular kernel is going to work for this set of data points? You can definitely, by trial and error, find this. But again, it's not a trivial or a straightforward problem, right? And so what we will now see as we move further along is that these neural networks have this nice ability to be able to capture these complex input-output relationships through a cascade of these neurons. Okay, that's the main takeaway that I would like to have for all of you at this point. Okay, if the motivation is clear, let's move on and see what a neuron does and how it helps in such cases. So just as a way of summarizing what we have said so far, these are all the points that we have made, right? So we have the supervised learning problem where we have a data set containing input points and the corresponding ground truths, right? So these are what we call our labels. And as you all already know very well, when the labels are discrete or categorical, we call it a classification problem. And when the labels come from a continuous set of points, we call it a regression problem. And like we've been saying so far, we want to be able to find a prediction for our input. And our theta is the parameter set of our model. Okay, and like we've also been saying, during training, we end up finding a theta that depends on our training samples. So again, if you notice, I think I slightly changed the notation. We have cap n points in our data set. We use little n points for our training, and then we validate our model on the remaining points. Okay, that's essentially what we want to do in supervised learning. We've also said this, we quantify the error between the prediction and the ground truth. And we try to minimize our model, the parameters of our model on this loss function. So I'm calling it R theta here. I think we've said L theta, you can use that interchange. And like all of you correctly also pointed out, how good is our model? We evaluate whatever theta star that we get here through this minimization problem over some set of parameters. We see how well the model is able to perform on our training, on our test set, excuse me. So that is essentially what we would like to do. And like you've all correctly also said, you've covered a whole bunch of models so far. And you've looked at all of these different types of classifiers perhaps. And we also very briefly saw what an SVM does, only visually. And what we want to now look at is another class of models, which we will call neural nets, which is going to be powerful in what it can achieve. So we've also talked about modeling the neuron right at the beginning of our discussion. And we want to also, at this point, I would like to also give you a simple, another example. We saw the image example, where we saw that the input-output relationship is not very obvious, right? So the other standard example that you probably have also seen, which motivates, neural network, is the standard XOR gate. Okay, so this is what I have here is the input-output relationship of an exclusive OR gate. Okay, and for those of you that may not have a background in electronics or in computer science, this exclusive OR gate is a binary gate which accepts 2 inputs and it gives 1 output. Okay, so what it does is that if you look at what the gate is doing, when both the inputs are identical, the output is 0. And when both the inputs are not identical, the output is a 1. Okay, and so for the case where you have 2 bits as the input to your exclusive OR gate, you have 1 output. And so clearly we have a function here that accepts, say let's call it x1, x2 if you want to write it explicitly. And this is the function that represents our exclusive OR gate. And the output is going to be the exclusive OR operation applied to the input data points. Okay. Now, in this case, if we were to apply a linear model to capture this type of behavior, you will see that a linear model will not be able to essentially learn this type of input-output behavior. Okay, and so if you were to simply say that I have some, say if I have my W hat, which is some W1 x1 plus W2 x2, and if you want to now measure the input-output relationship, or if I were to measure the distance between Y and Y hat, where my Y is defined in this fashion, you will see that our error is going to be high. Okay, this example again, I want you to see in the same light as we saw the example for our input-output. I introduced this more easily relatable example first, especially if people in the class are from varied backgrounds. This is something that's very obvious for you to see and tell that this IO relationship is not so clear or not so obvious. Now, the same type of relationship we also see for this simpler example, where we have this binary input and we have an output that is defined according to the exclusive OR relationship. Okay, so how do we build a model, or can we? This is the question. Can we find a model for the exclusive OR gate? Well, the answer to that is yes, and through a neural network. Okay, in tomorrow's lab session, you can see how you can essentially train a very simple neural network to learn this input-output behavior. Okay, so we've now kind of set ourselves up to understand what this neural network is. Okay, and I've also briefly mentioned this to you earlier. Now let us slowly start to formalize what a neuron is, and then what a neural network is. And quite obviously, a neural network is nothing but a network of neurons. And here we are obviously talking about artificial neurons. Okay, so let's go ahead and say first what a neuron is and how we can define the various operations that it performs on its input. Okay, so let's go ahead and now slowly start putting these things together. Okay, So let our input as always be X and let our output be Y hat. Okay. And again, if you've been observing what I've been writing, I've always been saying Y hat for the model output. Okay. And any reasons why I'm always calling it Y hat and not Y?
It is a
Because
vector.
y is the ground truth and y hat is not actually the exact value that we get.
Very good. So you're almost there. Yeah. There's one other person trying to answer. Please go ahead.
So it is a predicted value on the dependent variable.
Very good. So both of you are absolutely right. Y hat is a prediction that we are making. Okay. For Y, we do not have access to Y when we are doing, the inference, for example. All we are doing is, given an input, we are trying to predict what the output is, and that's why we call it Y hat. Okay, so please keep this in mind. And also the fact is that in all of these supervised learning models, you are trying to find the distance between Y, which is the ground truth, and Y hat, which is the prediction. Okay, you have, I'm sure you have seen this earlier also, but I'm just trying to reiterate the point. That's all. Okay, so now let's come back to our neuron, right? And before we go ahead and define the expressions, please keep in mind that a neuron at a fundamental, level is a composition of two functions. Okay, so let's call our function f to be a composition of, say, G and H. So what do I mean by this? So I first apply H to my input, and then to the output of H, I apply G. Okay, so we will see what this H and G are. And that is also written out here effectively for us. So this becomes our H, and this becomes our G. Okay, so I'll write everything in one dimension for simplicity, and the same thing applies for higher dimension input as well. So here, okay, I think I already have multi-dimensional input here. So let's write it for the vector case. So here the underbar that I have corresponds to a vector. Okay, so here let's say that I have x1, x2, x3, x4, and x5. Okay, so in other words, what I mean is that my x vector is composed of these elements: x1, x2, x5. Okay, now the first thing that we do is the linear operation. So this is the linear operation. And this is pretty much like a very simple, say, linear regressor, for example, that you have seen. Okay, so what this does is, to each input that I have a corresponding weight. I assign a corresponding weight. Okay, and in a neural network, we also have what is called as a bias. Okay, the bias has, again, useful properties. We'll perhaps get to that a little later. And then subsequently, we have the non-linearity. And this, like we've been alluding to earlier, is what gives it the strength. And when I have a cascade or a composition of several of these neurons, the effective capability of the neural network to capture these complex IO relationship becomes very, very high. And that is also the fundamental reason why deep neural networks have become so successful. We'll get to that slowly. Let's not get ahead of ourselves. Let's first complete what we started out here. Okay, so let me maybe write this as y hat linear portion is that. Okay, and finally, the y hat is the final output that we get from the neuron, which is this non-linearity applied to the linear function that is applied to my input. Okay, so if you want to put it together, we can write it as summation wi xi, I going from 1 to 5 in this specific example, plus w naught. So this is our bias term. And sometimes what people also do is, instead of saying x underbar, people also say x prime. And what they say is that they were going to introduce a 1, x1 through x5. And what they say is that this w naught that I have here is going to multiply my 1. So you can write it more compactly in this fashion. So this can be written as summation wi, say xi prime, I going from 1 to, say, we'll call it 0 to 5. Okay, so this is called x naught. So it's just a matter of notation, that's all. You don't have to be too worried about that. But sometimes people write this in this fashion, and people also sometimes write it in the vector form. So you will also see the output written in this form, w and x prime. Okay, so this is the inner product notation. So nothing but element-wise product of two vectors. That's all we are saying. So here in this case, my w prime is nothing but this vector, w naught all the way to w5. And all you're doing is you're taking an element-wise multiplication of these two vectors, which is captured through this inner product notation. Okay, now an obvious question that you will ask me is, what is sigma? Okay, and the sigma is, like I've been saying a few times already, the sigma is what is going to give a neuron all its extra capability over and above the linear portion of this input-output relation. Okay, so there are numerous choices for the sigma. But before we again start to discuss these choices, I would want to state to you why we want to have a non-linearity in the first place. Okay, and let us say look at the classification problem, a simple binary classification problem. Okay, so in the binary classification problem, you know that your label is going to be, say, either a 0 or a 1. Okay, and what we want to do is we want to map our input to either a 0 or a 1. Okay, so one of the fundamental motivations for us to introduce this nonlinearity, at least if you go back historically, what people wanted to do was they wanted to be able to map an input to either a 0 or a 1. Okay, and they wanted to do it in a manner that had some interesting and useful mathematical properties. Okay, so if you again go back a few years, what people said was that if I have to achieve, this type of a mapping to a function that takes either a 0 or a 1 through this nonlinearity, what we can end up doing is maybe if I have a function that is, say, x here, and say that the mapped function is f of x, which we want to essentially be either a 0 or a 1. People ended up using, functions like, let me use a different color just so you see it clearly. They ended up using functions that looked
Sir, isn't it a sigmoid function?
Yeah, I'm just trying to give you the motivation for why nonlinearity. Yes, you're absolutely right in what I'm trying to plot here, but I just wanted to motivate why we want to have this nonlinearity in the first place, especially when we have the categorical case of labels. Okay, so we want to end up having a function that takes values, 0 or 1 most of the time, and only in this small range of x is it going to vary somewhere in between. So that is one of the main reasons why we want to have this nonlinearity, especially when we want to solve a classification type of a problem. And going back to the observation that you just made, yes, you're absolutely right in what you said, that this function that I have drawn here is what is typically called as a sigmoid function. So here, this takes this particular form.
Sir, if it's a sigmoid function, then we can say this is as a logistic regression, right, sir?
You could effectively say it that way. Yes, you can do that. But what happens is I simply have one neuron here. When we have a cascade of neurons, you will end up with an effective input-output relationship that's going to be a cascade of such functions. Yes, your observation is absolutely right. Okay, and this is just to, like I said, motivate why we want to have a nonlinearity. Okay, if we want to solve the categorical problem, we want to ultimately map our input to one of these, say, two possible outcomes or outputs that the input can potentially have. Okay, now this is the standard sigmoid, like you correctly said, but this is not necessarily the only nonlinear function that we can apply in a neural network. You could have a variety of other functions that have, again, useful properties. What are these useful properties? We'll get to in a minute. Okay, but I'll again take a pause here and see if you have any questions about how we have defined our neuron itself. So just a quick recap. So we said that our neuron is going to be considered as a cascade or a composition of two functions. One which applies a linear operation on my input, followed by a nonlinear operation on my input. Okay, and this nonlinear operation is applied so that we can map the output of the linear portion of the function to these quote unquote binary values. So it could be a 0 or a 1. Okay, and we looked at a simple example, which is a sigmoid, and I would like to reiterate that sigmoid is not necessarily the only nonlinearity that we can use to construct a simple neuron. You could have other examples like a tan hyperbolic function, or what is more popular in the community of late has been the rectified linear unit and its variants. Okay, but again, the reason for the nonlinearity, I hope, is also clear to all of you. Okay, so shall we move on?
Sir, I have a question.
Yes, please.
So here y belongs to either 0 or 1. It is binary classification. So
yes, ultimately that's what we want. But yes, so we do have
What
Yeah,
my
go.
question is, when it comes to the above example which you were explaining, the cat, uh,
Right.
that
Mhm.
one.
Mhm.
In that example, the 0 or 1 represents whether it is a cat or not a cat, uh, or does
Okay.
the y
So
belongs to category?
okay, that's a good question. So here I have assumed that we only have two categories in what uh, in this particular on this particular slide. But if I were to go back to this slide here, yes, we could have a discrete set of outputs, and there what we do is that we try to look at the output at the output layer and then map it to a set of what we call as probabilities through what is called as a softmax operation. So to answer your question, in this case, we have multiple classes on this slide, and a 0 or a 1 corresponds to the labels of maybe the cat and the bird class, but that's not the only set of labels that we can have. And to answer your question, 1 does not mean that it's not a cat. 1 actually means that it's a bird, if that's what you are asking.
Yes, sir.
Yeah. And we could have, in this example, we have 4 classes instead of the 2. And again, since we are only operating at the neuron level at this in this slide here, I felt that a simple example like this should convey the meaning or the utility for or the motivation for describing the nonlinearity. That's all I meant here. Okay, does that answer your question?
Yes, sir.
Okay. Okay, so let's move on then, and let's go ahead and see what happens next, right? So now that we have defined our fundamental building block of our neural network, which is a neuron, we will now have a network of these to see how they can help us in coming up with a class of functions. Okay, so just to again recap, so you have seen a bunch of these different models. So what we are now doing in this session is we are adding to this list a neural network. That's what we're doing here. Okay, so let's move on and see if we can recap what we have done. So this is the motivation that we have this nonlinear IO relationship. And what are the properties of the sigma itself? By the way, this is just a representation for the nonlinearity, okay? So clearly it is nonlinear. It's continuous. And this differentiability, I have a question mark, especially when we come to this class of rectified linear units, okay? By the way, why am I asking this question about, continuity, first of all, and importantly, differentiability of our nonlinear component of the neuron? Why should we be interested in the sigma being differentiable or not?
Sir, sigma is just a function so that it classifies the data, right? So there is no point in differentiating it.
Can you go back to what we said earlier about finding the optimal parameters?
But optimal parameters can be obtained by differentiating the cost functions.
Correct. Yeah, can you build on that thought?
Sir?
Can you build on what you just said, whether differentiability is useful or not for our sigma function? So this is what we want to do, right? When we want to
Yes,
find
sir.
the optimal theta. And so what is the set of theta that's going to minimize this loss function? I'm sorry? Can you please say that again?
No, sir, that was the resound.
Okay, so coming back to our question about differentiability, maybe let me go further back. This is what we want to do, right?
Yes, sir.
I hope you're seeing what I have just boxed. So this, correct? So now can all of you try to go back and see if the question about differentiability is important or not?
But this is the cost function, no, sir.
Yes,
This is the linear function.
fine, okay.
But
So, yeah, go ahead.
sigma is a non-linear function.
Okay,
So far, which we have covered, we like as far as I remember, I never differentiated a non-linear function.
okay. But is our nonlinear function figuring in our y hat?
Sir?
Is our nonlinear function. So here, if you go back to what we just wrote for a neuron, so this is going to be our label now, correct? The prediction
Yes, sir.
of
Y hat.
our label, correct?
Yes, sir.
So if we were to measure how good or bad our y hat is, what do? We again apply some measure, some distance measure, like that,
Yes, sir.
correct? So
Yes, sir.
when I have to apply this, I essentially am going to replace my y hat with this,
Yes, sir.
correct?
Yes,
And
sir.
this, if we want to go back to how we defined L theta, it's going to be like that, correct?
Yes, sir.
I measure the loss over each of the data points that I have in my training set,
Yes,
correct?
sir.
And what do we do next? We do that, correct?
Okay, sir.
And
got
so
it.
when we are going to find the optimal theta, we want to differentiate our loss function with respect to the model parameters, correct? This is true whether you are looking at a linear model or a non-linear model, okay? And so when we now have the sigma appearing in our y hat, right? Then when we want to find the optimal parameters of the model, we have to ensure that our sigma is differentiable with respect to the model parameters.
Yes, sir. Got it.
Okay, is that clear to everyone as to why we are interested in this question specifically?
Yes, sir.
Okay, so the long story short, sigma appears in our prediction, right? It's going to be the y hat that we end up with is going to be sigma applied to the linear operation on our input. Okay, so when we are trying to find the optimal theta, we are going to differentiate our loss function with respect to theta, and the loss function itself is going to have our prediction in it. So in other words, the loss function is going to have sigma in it. And so when I have to differentiate the loss function, I have to ensure that the sigma that is going to be used for predicting my y is differentiable with respect to the parameters of my model. Okay, so that is why what we end up using for our nonlinearity is important. We need to make sure that at most places, our function, our sigmoid is our nonlinearity, excuse me, is differentiable with respect to the model parameters. Okay, am I clear in what we have said so far?
Sir, I have a small doubt.
Yes, please go ahead.
Sir, here we said that we are using non-linearity if there will be any existing non-linearity in the function, like in the actual data set. But then what
Yeah,
if we can?
yeah, go
Sorry.
ahead, please. Sorry.
what if we can use it, like what if the data set can be classified with a linear function? Then how does this non-linearity affect?
Yeah, that's a good question. So in such a case, what we end up doing, so again, say if you were to look at the the figure that I have here, right? So the sigmoid actually does behave like a linear model in this range, right? So if you were to plot it, you will see that in some small range, about 0, you are going to have this linear behavior. And you will also end up seeing that the weights that you end up learning are going to push the input to this linear range so that you are still able to capture the linear input-output relationship that is present.
Okay, so
That is in this case. Now, if you have something like a rectified linear unit, then clearly when you don't have negative inputs, you are simply going to have a simple linear input-output relation. And similar for the tan h function as well.
okay,
It's a good question that you asked. So I guess what you're intending to ask is this going to be an overkill when our input-output relationship is simple, right? I guess that's what you wanted to ask. Yeah, that's a good question. It should be reasonably handled in the case of a neural network as well.
Okay, so thank you.
Any further questions? Okay, so just by way of recap, I'm just going to write out the input-output relationship just one more time. Or you tell me, since you haven't seen since the previous slide is not visible. If X is my input to my neural network, what is going to be Y hat to my neuron? Excuse me. Let me not get ahead of myself. What is going to be the output? So what goes in here and what goes in here? Please don't look in your notes also. Can you just tell me without looking what Y hat is going to be if X is the input? So let's say that my X vector is the input to my model.
Sigma is the
Sigma
first,
X.
Sigma.
WIXI
Okay, very good.
plus X naught.
Okay, so
X
let me capture that
W.
here.
Yes, sir.
Okay, and I go from say that I have P input. P is the dimension of my input. Okay, very good. And I also say here that my X is composed of 1, X1, all the way to say XP transpose. Now, what is my W vector? That's going to be composed of W0, W1, all the way to. Okay. And we have one more blank here.
Key function.
So what goes in here? What is the function
then-
that acts on the linear output?
Sigmoid function.
Right. So I just use this as a placeholder. Like I've said, the nonlinearity could be any of these. Okay. So this is how we can explain or define, rather than explain, how we can define the IO relationship of a simple neuron. Okay, I think this is now clear to all of you. So the next step from here is to see how we can work with a bunch of these neurons, okay? To, again, see how we can map the input of our data set to its corresponding label. Okay, that's what we will do next. Okay, are you all with me so far?
Yes, sir.
Yes, sir.
Yes,
Okay,
sir.
very good. Excellent. So let's move forward and see now how we can construct a neural network. Again, nothing fancy or nothing surprising that's going to happen. We simply have a neural network. Here what I have is what is also called a multi-layer perceptron. So this is sometimes also called a perceptron, whatever I wrote as a simple neuron. It's also sometimes called a perceptron, and we have multiple of these. So this is our input layer. So this is our x1, x2, all the way to say xp. Okay, and each of these is a neuron that I have here. So this is usually denoted by Z or Z, and this is our output. Okay, and in our image labeling problem, we had k equal to 4 in that case. Okay, so this Z, as I call it, or Z, is what is our neuron. So again, just to reiterate, so this is going to be defined in this fashion. Zero to P, and I'm going to also introduce one more notation here, just for consistency. Okay, so here what I mean by this is I have the weights. Let me start to also write out the weights that connect my input to each of my neurons. By the way, before we go ahead, notation wise, this is obviously called the input layer of my multi-layer perceptron or a simple neural network. Then I have what is called as a hidden layer. And finally, I have what is called an output layer. Now, if you want to, and this is perhaps the simplest of the neural networks that one can construct. Okay, I only have one hidden layer in this particular network configuration. Okay, when people start talking about deep learning, they essentially introduce more hidden layers. Okay, so here I just have one. As I have more and more hidden layers, the depth of my model increases. And because we again have a composition of functions, that composition of functions is what is going to allow for complex input-output relationships to be modeled through this nonlinearity that I have. I will discuss this also in a little more detail a little further. Okay, so now this Z1 is the first layer, first hidden node in my hidden layer. Okay, and there is also a reason why this is called the hidden layer. The reason is that this hidden layer, obviously, as the name itself suggests, is hidden from the user. The user is not directly going to be able to see what is happening in the hidden layer. The user is going to give the input and see the output without really worrying about what is happening in between. Okay, so any set of neurons that are going to appear in between the input and the output. So any neuron in this, within the input output set of neurons is going to be called a hidden neuron. And a hidden layer is nothing but a collection of these neurons. Okay, so this is the nomenclature of a very simple neural network. Okay, now let us start to be systematic in how we are going to define the parameters and the terminology, the notation to be precise, of the various parameters that go into a neural network. Okay, and before we do this, if we go back to our neuron itself, in this case, how many parameters did our basic neuron have? In this specific example, where I have 5 inputs to a neuron, how many parameters did we end up having in this neuron?
5 parameters.
6.
5 and
Six,
6.
six,
I
six.
got 2 answers. So, which is, so how many parameters do we have in this case?
6. 6.
So essentially, we have 5 of these weights and we have 1 bias. Okay. So if we were to look at all of these together, like you said, we are going to have 6 parameters in all, out of which 5 correspond to the weights that we multiply to the input and 1 corresponds to the bias. Yeah, so good. So that's what we have for a given neuron. Okay. And here, since we have a neural network, let us be, again, like I said, systematic in how we are going to label our parameters, because that is going to be important as we do further analysis of our neural network. Okay. So now what we are going to use, at least in this today's discussion, the notation that we are going to use is as follows. So when I have a connection between an input node and a neuron in the hidden layer, I am going to use the following notation. I'm going to use W as the weight that connects the first input node to the first hidden layer node. So the notation is going to be the target is going to appear first and then is the source. So this weight is going to have the index 1, 1. So now, if I were to use this notation, can you tell me what is the notation I will use for the weight that connects the pth input node to the first hidden layer node?
P1.
1p, sir.
1p.
So like I said, the target is going to be the first index and the source is going to be the second index. Okay, so like several of you correctly said, this is going to be 1p. Okay, and if you want to also use the same notation for the bias here is going to be 1, 0. Okay, and that hopefully is already captured here. Okay, so if you see, I call it W1I, correct? And that is going to multiply xi. Okay, and the same notation as before. So my vector x is going to be composed of x0 all the way to xp. And if I were to look at the vector corresponding to the, say, the mth node here, so let me call this, instead of 2, let me say call this m. Okay, so can you tell me how this m vector is going to be populated? It's going to be a vector of weights, obviously. So what is the first element of this vector and the last element of this vector?
W10 and W13.
So this is my target node, right? The target node index is m. So what would be the bias notation that we'll be using here? What would be the index for the bias term?
W1M.
M0.
W?
M0.
M0.
Very good. Excellent. Yes. So this is going to start from WM0 And what is going to be the weight that's going to connect the pth input node to the mth hidden layer node?
WMP.
Excellent. Okay. Okay, are we good? Are we clear with the notation that we will be using? Okay, and maybe to be consistent with what we'll be using further, I'll replace this W with alpha. This is just to be consistent with the notation I plan to use down the road. Okay, so I'll call it alpha instead of W. And this is going to be everything else is the same, just that I'm using alpha now instead of W. Okay, nothing else changes. Now, by a similar, in a similar fashion, can you tell me if I use beta for the weights that connect my hidden layer node to the output layer node, can you tell me what is the notation I will be using for this link, the weight that is going to connect the kth output node to the mth hidden layer node? So it's going to be beta
K.
Very good. Okay, so again here we could end up also having similar bias terms, which we'll say call beta 10, and this bias term is going to be called beta k0. Okay, now if I were to similarly define the vector beta little k, it's going to be populated in a similar fashion. So I have beta k0 all the way to beta k. Can you tell me what's the index here?
Capital M.
Excellent. We have capital M. Okay, so are you all good? Are you with me so far? Just only notation is what we are introducing. Okay, and let me also tell you why we are doing this. So we are doing this because at the end of the day, we want to find what these optimal alphas and betas are going to be for a given problem. Okay, and so that's why this notation, and subsequently as we're going to talk about backpropagation, it's important that we have our notation in place and consistent. So just to repeat, the indexing is going to be it's going to be a tuple again. The first is going to correspond, the first index is going to correspond to the target node, and the second index is going to correspond to the source node in our network. Okay, again, I'll pause here and see if you have any questions. Okay, so if there are no questions, let us also do one more thing before we get into analyzing this network for error and minimizing error. Okay, before we go there, now we have a model now, right? We have, this is going to be the prediction. Again, to be consistent, let me call this y hat instead of y. And you all know the reason for that. Now let's see what are the parameters that are associated with this model. Let's just simply count them out. Okay, so we have the alpha vectors and the beta vectors that correspond to the parameters of this neural network. Okay, so can you simply help me count them? So I have alpha 1 through what? Through alpha. And similarly, I have beta 1 through beta. Can you please tell me what the index here should be and the index here should be?
M, sir.
Alpha capital M, beta K.
Excellent. Okay. Now, can you also tell me the count, meaning the cardinality of this set? How many parameters am I dealing with here?
M plus K.
Please look at it node wise. Okay. For
Two
a
parameters.
given hidden layer node, how many parameters are we associating with it?
P parameter.
That's what we have here, right? So how many parameters do I have in this vector? So alpha little m has how many elements in it, this vector? In other words, what is the length of this vector here?
P, sir.
P.
Just a little careful.
P plus 1.
Excellent. So we have p plus 1. And how many such alphas do we have?
M alphas.
Excellent. So then how many parameters do we have corresponding to the alphas?
M into P plus 1.
Excellent. So we have m into p plus 1. Okay. Similarly, how many parameters do we have corresponding to beta?
K into M
K
plus
into M plus 1.
Excellent. Excellent. Okay. So these are the number of parameters that we have. For a simple neural network that has capital P input elements, capital M hidden nodes, and capital K output nodes. Okay. There's a reason we are writing this out as well. We'll come back to this reason in a few minutes. Okay. So this is the setup that we will be using for the second half of our discussion. Okay. So I think we started around 4:10 or so, 4:10 or 4:15. So we are roughly 1.5 hours into the program, into the discussion today. So if it's okay with the AIET team, can we take a short break now and come back?
Yes, sir.
Okay, so it's about 5:55 now. We'll take maybe a 5 to 6 minute break and we'll come back around 6:02 or 6:03. Okay, and then we'll continue our discussion. And if you have any questions, the moment we come back, I'll be happy to answer any questions that you have. All right, if we are ready, we can continue. Shall we go ahead? I hope you can still see my screen.
Yes, sir.
Okay, great. So let's continue then. All right. So what we have done so far is we have motivated the necessity for a nonlinear machine or a nonlinear model. And we have set up the groundwork for analyzing a neural network. So to do this, we first of all defined what a neuron was. And then we put a collection of these neurons together to form a simple neural network. We have precisely defined what the input-output relationship of a neuron is, and therefore what the input-output relationship of a neural network is going to be. So we've also along the way defined the notation for the weights that go into a neural network. And we will soon start to write out the input-output relationship of a neural network. Okay, and why we want to do this is because ultimately we want to be able to find the optimal weights of a neural network with respect to a given training set. So that is going to be the next set of steps that we'll be carrying out. And along the way, we will also come across what is called as the backpropagation algorithm. So that's the agenda for the second half of our discussion. Okay. And before we move further, any questions about what we have set up so far? So we have identified what are all the parameters that go into this neural network. We have counted how many there are, how many parameters there are in our model. If you have any questions, please feel free. If not, we will proceed. Okay, so let's go ahead and now write out the input-output relationship in this network. Okay, and I'm now calling it a feed-forward neural network because there are also instances where there can be feedback loops in the network. We will not consider, networks that have feedback loops in them in our discussion today. Okay, it's an interesting discussion that deserves its own attention. But for now, since it's introductory, we will not talk about networks, neural networks that have feedback loops in them. They're recurrent neural networks, have lots of applications, but not for today. Okay, our next step is now to write out the input-output relationship in our neural network. Okay, so I'll simply recap that we have, say, xp input nodes in our network. We have z1, so let me call this z little m, and z cap m, and we have y1 hat through y cap k hat. Okay, now just like we saw in the input-output relationship for a neuron, a simple neuron, it's composed of the linear operation applied to my input, followed by the non-linearity that's applied to the output of the linear function. Okay, so what we now want is y hat in terms of x. Okay, and why do we want this y hat related to x? What is our motivation?
Sir, can you repeat the question?
Yeah, the question is, I now want to write out how y hat is related to x explicitly.
Y
So I'll
hat
write
is
out the,
sigma
yeah,
of,
please go ahead.
sir, y hat is equal to sigmoid of sigma I0 to capital M.
Okay, go ahead.
Xi and Wi.
Fine. So this is, we will write it out in all the gory detail in just a minute. Okay, but my question is why? Why do I want to do this? I want to do this because my input and output is related through this function, correct? And it is composed of the parameters and the input, correct? And through our training process, what are we trying to do? We are trying to find what the optimal parameters are for my function that's going to minimize some loss, right? The motivation remains the same. The motivation is that if I know my input output relationship, right, then I can compute the prediction for a given input, correct? And since it's a supervised learning setting, I can then compare my prediction with what?
Ground truth.
Exactly. So in order for me to do that, I give my input to the model, I compute y hat, then I'm in a position to compute the error between my prediction and my ground truth, right? So in order for me to compute the error between the model output and the ground truth, I need to know the exact input output relation. Okay, that's the reason why we want to do this. And once we know the error, it will help me find parameters of the model or update the model parameters so that what happens?
The error decreases.
Exactly. So that the
Optimize.
error decreases. So in other words, I am able to train my model so that the training error is going to be reduced. Okay. So to achieve this goal, we first of all want to have the expression that relates my input to my output. Okay. I hope this motivation is clear. Okay. And it's not a complex expression. We just have a couple of lines that we will write out. And then you will see for yourself that for a given input X, I know how the output Y hat is computed. And it is obviously going to depend on what? It's obviously going to depend on
Parameter.
Parameter.
exactly the model parameters, right? Am I making sense in what we are trying to do now?
Yes.
And this to again relate this to what we have seen earlier. We did this earlier also when we spoke about our linear model, right? So here, this F is nothing but mx plus c, where m and c constitute our model parameters, and y hat is mx plus c. So when I want to find this distance and the squared error, I replace my y hat with mx plus c, right? And this is what I will end up finding as the error for a particular choice of m and c. Identically, we are doing the same analysis where we replace this function with the neural network input-output relationship. That's all we are doing. And this is required for us to find the loss and then update the MNC to minimize our loss. Okay, I hope the motivation is clear as to why we would want to explicitly write out the input-output relationship for a neural network. Okay, if it is clear as to what our goal is, I will proceed. Or if you have questions, please feel free to ask. So we know here that our y hat, depends on the output at the hidden layer. Okay, and the hidden layer output depends on my input. So we'll go first from here to here, and then from here to here. Okay, so let's write out what the z is going to be. You all know this, we just wrote it out. So I'll pick an arbitrary node zm, right? So before I write out the expression here, can you take a minute? So this rest of this, the second half of today's discussion, I want you to please work out with me with pen and paper, so you follow exactly what we are doing. That way it will be clear to you also as to how we are analyzing the network. Okay, so can you please write out what the output here is going to be. So ZM, we know, is a neuron. This is, each of these is a neuron, right? So, and we also know what the weights corresponding to this neuron are going to be notated with. Okay, so what is ZM going to be? It clearly has a nonlinearity applied to a linear function, correct? So can you please write it and then help me also?
Sir, it's going to be sigma I is equals to 0 to P W M I Xi.
Okay, sigma. Okay, I have the little sigma, the nonlinearity. Then I will use the shorthand just for simplicity. So I will say that this is equal to
WM.
Okay. So here we
Like
have
alpha.
alpha. Very good. And
X.
okay, excellent. Okay. And what we will also do is we will bring in the data index. Okay. So this is for a given data point. Now I will index this like this. Okay. So this is going to be, say, ZMI corresponding to the data index. We will need this also. That's why I'm writing it out here. You understand what the data index is, right? So here I will, let me be clear about this as well. So the D is composed of Xi, Yi, right? And we have I going from 1 to, say, cap N. So for the ith input to my model, the output is going at the mth hidden layer node is going to be notated like this. So this is the hidden layer node index. Okay, are we clear? And if you wish, I mean, if you want to avoid confusion, what I will also do is I'll put this as a superscript instead of a subscript. Okay, so this is the data point index. Okay, are we good?
Yes, sir.
Yes.
Okay, fine. Now this is okay. So we now have the output here. So we know what the ZM is going to be. Excellent. So ZMI also, let me put it. Okay. Now we know that the output. Now I'll first describe how we are going to get the output at the output node. Okay. So what I'm saying is now YK. This I will write out just to. I'll first write it out and then I'll explain to you what I mean. So this YK is going to be equal to the softmax, okay, of the output vector. Let me call it maybe some T. Okay, this is the vector T, and the softmax at K. I'll tell you what I mean by this. Okay, so this T is a vector corresponding to the output at each node. So let me say T1, and this is Y I hat to be precise. Okay, and here my TK I will write out as the inner product between beta K and Z. Okay, and softmax itself, K of T is defined as e to the Tk divided by summation e to the Tj, j going from 1 to cap K. Okay, so what do I mean by this? I'll go slowly Please feel free to stop me at any point. So the y hat, since we are looking at the classification problem, we are going to convert the outputs to probabilities. Okay, and we do that. It's a standard operation. Some of you may have already seen it, or most of you may have seen it. We apply what is called as the softmax function to the raw output. Okay, the raw output is defined like this, just like we defined, the and maybe I will also use this. Okay, so the raw output is nothing but the inner product. So we are looking at, say, the y at k, right? So the raw output at the kth node is defined by this capital T, little k, and the data index I. And that's nothing but the linear operation. Okay, so this is what we have, beta k0 to beta k capital M, right? That multiplied by the each of the outputs at the hidden layer node. So this is the linear portion of my output. Okay, but this is raw in the sense that it is not normalized and it doesn't say add up to 1. But since we want to do, categorical outputs we want to come up with, we convert this vector. So I'm going to have now T1 through Tk for sample I, for input I. So this is what so this is the raw output that I have. Okay, so this is equal to Ti, the vector. Now this is converted through my function gk for the kth output node, and this is nothing but my softmax function. So all it does is it simply weights. So if you see what is going on here, so I take the relative weight of e to the tk over all of the outputs all of the raw outputs. Of course, it is raised to the e raised to that particular raw output. Okay, so this is what is going to be the output. So let's number this equation 1 and equation 2. Okay, I will pause here and see if what I have explained is clear to you. I can also maybe call this GK just for simplicity. Let me call this GK. And this GK is nothing but our softmax.
Sir, what is T here?
T is this intermediate output. Maybe I will, this is the raw output that I get. So now what is happening? So let's look at a particular node K here. So let me call this the kth, little kth node. Okay. So what happens in this is that we again apply a linear operation to the output of the hidden layer. So each hidden layer node is connected to the kth output node. Okay. And so there are weights, and those weights, as we know, are going to be captured in this weight vector beta k. Is that clear? So the beta k connects each of the hidden layer neurons to the little kth output node. Is that clear?
Yes, sir.
Okay. Now, what does beta k do? It essentially multiplies each of the output, each of the hidden layer node outputs. Okay. So that's what we are capturing here. So the z vector is nothing but the vector of all the hidden layer outputs. Okay. Now this I call quote unquote raw because it doesn't have some of the useful properties that we would need when we are solving the classification problem. Okay, so in order to convert the raw output, so this is the raw output that I have. So to go back to your question, TK is nothing but the raw output that I have at the kth output node. And when I collect all of this, so T1I to T capital Ki, that is going to give me my vector capital T. Is this clear?
Yes, sir.
Okay. All of you,
Sir,
please take a
after
moment
collecting-
also. Yeah, just one moment. So just make sure that there are no errors in what I have written. Just review everything, because this is what we will build on to come up with our backpropagation algorithm. Yeah, there was a question. Please go ahead.
Sir, after we have computed all these raw outputs, then we are applying the softmax function so that we get the final output, right?
Correct. Exactly. Yes.
It will be applied for each node or each
Correct.
node in the hidden layer.
So this is going to be applied. So we have the raw outputs at Y. So at the output layer, if we don't choose to use the softmax, all we are going to have is the T, the vector T. Okay. But since we
Yes.
are operating in the classification setting, we want to somehow normalize, like some of you were mentioning earlier, we want to normalize the output so that the output sum up to 1. And that looks like a probability, distribution. But let's not worry about probability and stuff for now. We simply want a useful property in our output vector. That's all we are doing through the softmax operation.
After applying the function, we'll be getting the final probability.
Correct. So the yk that we have here is essentially going to be, probabilities corresponding to each of the k classes. So we have capital K classes, right? Going back to our image example, we have 4 classes there.
Sir, here, how do we know the dimension of the hidden layer? Like M, capital M. It can be.
Yeah, that's again, something that we choose. It's a trade-off in many cases. So you can choose, if you end up choosing a very large M, obviously, like we calculated here, that's going to immediately impact the number of parameters that we have in our model, correct? And so if we don't have too many data points, it could lead to issues like overfitting, right? So it's again, a short answer to your question is it's chosen empirically, and it depends on the number of data points that we have.
Okay, sir.
Okay, so is the I/O relationship clear? So now we can go from the input X that we have here to the input X that we have here to the final class probability that we have here. Okay, and many times people do things like one-hot encoding, wherein you say that if my input is a cat, right, and the cat is a 0 class, then the vector label will be a one-hot encoding, meaning I will have a 1 in the 0th or the first location of my vector, first position of my vector, and the other elements of that vector will be 0. So we then will train the model so that certain loss between the y hat vector and the y vector, which is one-hot encoded, is minimized. Okay. So we will probably see that in the demo session tomorrow as to how the one-hot encoding can be used to train the model. Okay, but importantly, these two equations that we have, in equation number 1 and 2 are simply going to relate my input output. Okay, so let me call this equation maybe 3. So if I plug in 3 into 2, that's going to connect my x to my y through the parameters that we have here. So this is one set of parameters. This is another set of parameters. So therefore, what we have done so far is to explicitly relate the output of my neural network to my input. Okay, is this clear now as to what we have done? I'll just again pause for a few seconds. If you have any questions about any of what we have written, please feel free to ask. Okay, so if this is clear, that's very good. Now let's move on. So what next? So now we have an input-output relationship, and that involves the model parameters, just like other models that you have seen so far, right? So next question is, how do we train this model? That is the next question. So we have earlier also, we have said how we typically train a supervised learning model, right? How do we do that?
By reducing least squares, like we calculate the error.
Right, that was in that particular case. In general, if you want to abstract that, we have to define a loss function, correct? And we
Yes.
find the parameters that are going to minimize that loss function over what?
Predicted
So we
value and
train
actual
the
value.
model over what?
Predicted value
Over
and
what data points?
training data.
Exactly, over the training data points that we have, right? So now the next step in our process is to, first of all, define the loss function for this particular model. Okay, for simplicity, we will continue to work with the squared error, like one of you just mentioned a minute ago. We will work with the squared error. Okay, so let's see how we can write the loss function for this particular model. Okay, so let's start out by, first of all, saying that I want to compute my training loss over all of my training data points. For simplicity, I'm simply going to say that I will use n. I have n data points in my training set. Okay, or if we want to be consistent with what I had written earlier, I will say that this is maybe capital T. I'll maybe call it NT because we are using T again here. So let's not confuse. I'll go fix the earlier notation to reflect this. Yeah, I'll just call this here NT for the number of training points and capital N for the total number of points in our data set. Okay, now what we need to do is write out the training loss. Okay, so we'll write it in this fashion. I sum over each of the data points in my training set. Okay, and I'm going to look at the error at each of the output nodes. Okay, so I'm going to sum, say, let me call this K, going from 1 to capital K, the error between Y, I, K, and what? Can you please fill in this blank here?
Y cap I.
Excellent. So Y hat K I. Okay. Now we'll simply expand this. I'll erase this arrow. So this is going to be, and I do hope you're all at your end working this out on a piece of paper, just to make sure that the clarity is there. That's all. So here I'm going to say YKI Okay, so in other words, we are using squared error, and we can also bring in that 1 over NT here to call it mean squared error. Okay, so this is my L theta.
Sir, what
Okay.
is NT?
NT, like I said, is the number of training points.
Okay, okay.
Okay. Okay. So also, since we have written out the expressions on the left side, I'm going to erase some of the stuff I've written here. Okay, are you all with me so far? So now what we have done, since we know what YK hat is or Y hat is, we now want to define the loss and introduce YK hat into the loss and minimize that loss with respect to the model parameters. So clearly, like we have seen here, this Y hat is a function of both alpha and beta, which are our model parameters. Okay, is this clear as to where we are heading with this? Just like in the linear case, we simply have a slightly more complicated expression for Y hat. Instead of Y hat being mx plus c, we have Y hat being defined through our equation 2 and 1. That's all is the difference.
Yes, sir.
Okay, may I proceed?
Yes, sir.
Okay, very good. Now, the question is L of theta convex in theta? Okay, why am I asking this question? The reason I'm asking this question is, now if you see, I have like L of theta and I have like a square term here, right? So we would hope that if it is something like, you know, a quadratic function in my parameters, I can solve it exactly, meaning that I can come up with a closed form solution for my theta. Okay, so is this convex in theta? That's the question that I'm asking, and I'm a little, you know, I'm trying to be a little greedy here to be able to solve for theta very efficiently, and not just efficiently, we also come up. Can it give me an exact solution to the problem, to the minimization problem, right? So why are we asking this? Because we know that theta star is arg min. So what I mean by arg min is that the argument of the function that minimizes this loss function, right? So that is what I mean by, that's why I'm asking this question. Well, unfortunately, it's not a nice input-output relationship for this particular network configuration that we have, and it is so because of the nonlinearity that we have introduced. It makes L of theta non-convex in theta, and I have a small visualization to show you what I mean. So here I have an error surface that looks like this. I have taken just a small snapshot of the error surface. So if these were my theta, right? So if this were, say, some elements of my theta, let's say theta 1 and theta 2, and if the y-axis were my L of theta 1 comma theta 2, it turns out that I do not have a surface that looks maybe something like that. Okay, if I have a surface that looks something like this, then I can apply. So this would be a convex surface. But unfortunately, I do not have a surface like that. And so the consequence of this is that I cannot, first of all, come up with a closed form solution for this problem. That's one thing. The second thing of this, the consequence of this, let me just jot it down here. So L theta is not convex in theta. So implies no closed form solution. Meaning I cannot say, like, for example, in the simple linear regression type of examples, you know that you can apply the pseudo inverse of your matrix that connects your input and output, and you use that to find like a direct solution to your problem. That cannot be done. Okay, so even if it is not convex, it has no nice mathematical form that allows for an analytical solution to the problem. Okay, even if it's not convex, if it has some other form which is useful, I could have tried to exploit that formulation. But so first of all, I'll also write out the reason for this. This is due to the nonlinearity present in our model. So this is unfortunately a downside to introducing the nonlinearity. While it helps in improving the model's ability to capture complex input-output relationship, it has this unfortunate downside to it. So that is very costly. So what we then have to resort to is that theta star is not going to be global, meaning that I can potentially not find the global optimum to the problem. I can only find local minima through the minimization process. Yet another consequence of this observation is that I need to take an iterative gradient based solution to finding the theta star. Okay, so what I mean by this is that I have to take, update theta iteratively. So I will say that I have, say, theta r is equal to theta, say, r minus 1 minus some weighting that we apply to the gradient of my loss function. Okay, and this evaluated with respect to the previous set of parameters. So what do I mean by this? Since I do not have a closed form solution, I will first show this pictorially to you, and then we will discuss this. We'll write out the expressions. So what I'm going to say is that I will arbitrarily pick a theta. Okay, so this is essentially going to correspond to my choice of theta here. Okay, then what I'm going to say is that I'm going to descend along the negative of the gradient to try to reach this local optimum. Okay, so if I were to say that my theta r minus 1 is here, I'm going to compute the gradient of my loss surface. Okay, so the way you can think of it is that suppose that you have a hungry ant that is sitting here. Okay, so I have an ant that is sitting here, and this ant wants to, the food for this ant is at this, bottom here. There's maybe some sweet or some honey or something, and this ant is very hungry, so it wants to be able to go reach its food as quickly as possible. So the strategy that the ant is going to take must be, it must be careful. It shouldn't jump in the direction of the gradient very fast, lest it will keep bouncing on the surface. So it should be careful in finding the direction of the gradient, right, and head in that direction. And how big a step it takes is determined by this eta. Okay, so if it takes too large a step, so it may end up going that way. And if it ends up taking too small a step, it's going to take forever. So this eta term that I have here is going to determine how much of a jump or how big of a jump the ant is going to take in the direction of the local minimum. And that direction is given to us by computing. So this is the loss surface, right? So I compute the gradient of the loss surface around that point. So that's what maybe I'll write this here like this. So I'll write it like that. So I compute the gradient at my current position, and then I head in the negative direction of the gradient. So slowly, if my eta is small enough and I take these steps, the ant is going to end up at the local optimum. Okay, and this is an iterative approach. So I need to compute the gradient of my loss function over my iterates, and then use that gradient to head to the minimum value, the local minimum value. Okay, so this is the fundamental idea behind this gradient based update for the model parameters. Okay, so pictorially I have tried to illustrate this to you, and hopefully the idea is now clear as to how we can go about finding the local minimum through the computation of these gradients. Okay, I'll pause here and see if you have questions.
Sir, how do we find the exact parameter eta that it does not go far and it is not small?
That's again a good question. So for this discussion, we will not probably have the time to see what are the optimal choices for eta. I will point you to references, but this itself is an active area of research, and people have tried to propose several approaches to find what this eta is going to be. So for this discussion, we'll keep our eta to be a constant, but you can make it a function of, say, the previous gradients. You can use methods that are known as, say, momentum. So you try to keep, like I said, track of the past gradients that you compute, and look at their gradient magnitudes and use that to come up with a value for eta. And there is this adaptive ways of doing this as well. I'll point you to literature where you can read up on how they come up with different choices for eta. But for now, since we are more interested in finding the backprop, I'll only answer to this point. Nevertheless, I'll point you to material.
Okay, sir.
Sir, here the theta is learning rate, right, sir?
Can you please say that again?
Here eta is learning rate.
Yes, eta is the learning rate.
So
Correct.
actually, in our previous lab sessions, we have done on gradient descent.
Okay.
So here we initialize eta in the form of list of few value,
Okay.
and then we computed. Like, is it the same approach, sir?
Yeah, similar. But if you only had like a fixed set of values, you can experiment and see what is going to be helpful for you to reach the local minimum. But there are ways in which you can compute eta also in terms of the gradients, like I was mentioning just a minute ago. So you can even either have a fixed list or you can make it adaptive.
And this iterative gradient, it's related to the value of epoch.
Yeah, you can look at it that way. Yes, the current iteration and the previous iteration. That's what is going to be used in say these computations that we have here.
Sir, also, what is exactly a closed form solution?
A closed form solution is like where you have an exact equation that's going to relate your theta to the model parameters and the input values.
Okay.
Okay, so if I have like a pseudo inverse type of a solution, so if I have say y hat or my theta hat, my theta star is say some matrix times my input. Okay, so or say some matrix inverse times an input. So I know exactly if I have my x and my a, I know how to find my theta star.
Okay, understood.
Yeah, that is what is called as a closed form solution. Okay, so are we clear on the gradient approach to solving this problem? Because of the reasons that we have identified here. So we don't have a nice form for our loss function in terms of the model parameters. That's why we have to resort to an iterative gradient based solution to finding the model parameters. Okay, and we all know what the model parameters also are for the neural network. So they are essentially the alphas and the betas. So now the next step in our analysis is to actually see if we can find what the gradient is. That is this what we have written here. Can we find this gradient of L of theta? Okay, and once we find this, is there an efficient way to find the gradient? And that efficient way is actually what is going to result in the backprop algorithm. Okay, so that's what we are going to do in the time that remains. Okay, so let's go ahead and just recap what we said. So we are only going to find the local minimum because we have a non-convex problem. We are going to use an iterative procedure, like we just said. We are going to use the gradient and try to descend, using the guidance that we get from the gradient. And now let's finally derive the gradient update expression or the gradient expression and use it in the update equation. Okay, so now let's go back and look at our L theta. So L theta please look in your notes that you'll be making, and just make sure that I am not making any mistakes when I write this. Okay, so this is our loss function, which is our mean squared error. Now this I'm going to write in terms of our y hat. Okay, I'm going to expand my y hat. That's what I mean. Okay, so this is anyway the ground truth label, so I don't have any control on that. Minus here, if you recall, we wrote it like this. Correct? Just double check your notes before I go back and also check the previous slide. Is this correct?
Yes, sir.
Yes, sir.
All right. Now, this I'll just write out one more step. So this is essentially GK, and our T itself is going to be, this is a vector, right? I'm just writing that out. So this is, now if I want to write it in terms of the beta, and this is going to be Z. Is that right? So I'm looking at the kth, little kth element of my vector capital T. Correct? And the last element here would be beta cap K and Zi. Right?
Yes.
Okay, so this is now my loss function. Now, let's say that I want to look at, so let's go back to our neural network now. Okay, so now here we had written this, right? So can you tell me the label or the index label that I will associate with this beta? So it's connecting the mth hidden layer node to the kth output layer node. So what is going to be the index for this particular beta?
KM.
Excellent. So this is KM. Okay. Why am I asking you this? I'm asking you this because we now want to minimize. So let me complete this as well. Okay. So let me now try to find what this is. Okay. And let me also tell you why we want to, before we go here, maybe I just jumped one step. From here, from what we just said in the previous slide, we want to find this gradient, right? So this gradient, what does it mean? So when I say I want to find the gradient, so please note that Gradient L theta is obviously with respect to theta. So what is it going to be composed of? It's going to be a vector, right? So this vector is going to look like that. There's going to be each of the elements that we have in each of the parameter vectors. It's going to be composed of those. So I'm going to have alpha 1, 0 all the way to. So how many alphas do we have? So we have as many alphas as there are hidden layer nodes, correct? And so I'm going to have up to alpha m. So what's going to be the second index here? So alpha n, correct?
Yes, sir.
And similarly, I'm going to have more elements here in this vector. So this go from the partial derivative beta 1, 0 all the way to, I'll also bring in this element now, beta km all the way to okay. So this is how our gradient vector, this is obviously going to be a vector. This gradient vector is going to be composed of all of these partial derivatives. Okay, so we'll start out by trying to find this guy here. Okay, so we know what L of theta is. Now we want to find the partial derivative of this loss function with respect to one particular weight, which is going to compose our set of parameters theta. So we'll just pick one of these, and that is beta km. Are you with me so far? What I'm trying to say here. So we know that our theta, the model parameter, is going to be updated using the gradient descent method. And the gradient itself is going to be composed of a number of partial derivatives. And what we are now trying to find is the partial derivative of the error with respect to one of the elements of our parameter vector. And specifically, we have chosen beta km, that is the weight that is going to multiply the output coming from the mth hidden layer node when it is connected to the kth output layer node. Is it clear what we are doing now?
Yes, sir.
Okay, if you have questions, please feel free to ask. And like I drew just a minute ago, it is this weight. So let me maybe use a different color. So this guy. Okay, we want to see how this is going to influence the loss. That's all we are trying to find out. And the influence we are trying to find using the partial derivative. So if I change my beta km by a little bit, what is its impact on the loss? That's what we are trying to find. Okay, so let's go ahead and find it. So now I have one question for you before we proceed. So this beta km that I have, is beta km going to be present in the expression for the output here? Beta m going to be present here, beta km, sorry. Is it going to be present here in this node? Is it going to be present in this node? So in other words, what are all the output nodes where beta km is going to have a presence?
Only in one sir, the y small.
Exactly, right? Because it's the node, that's the weight that connects this node with this node. It's not going to be present in any other output node. Right? So I hope you see what I am saying. And why am I mentioning this? Because when we compute our output, when we compute our partial derivative, we don't have to worry about the beta km being present in any of the other output nodes. Okay, and so where is that going to reflect? It's going to reflect here, right? So when we are summing over all of the outputs, the influence of beta km is going to be seen only for a particular choice of the output. So let me write that out. So here, so this means that I only need to worry about one particular output node. So here, I really don't care about all of the other nodes. I only worry about correct. I can conveniently ignore the other nodes. I only care about this little k in my expression. Okay. And this is since beta km affects only yk hat. Okay, is this clear what I am saying?
Yes, sir.
Yes, sir.
Okay, now it's simple differentiation now. So this is nothing but, I'll just write it out. So I have a square, I have a function of a function. So I will have a term that looks like 1 over nt, summation I going from 1 to cap nt, negative twice yki minus yk hat I times the partial derivative of beta km yk hat I. Okay, so this is what we have. Okay. Now what we need to find is, now let's find so the question is, how do we find this? So this is nothing but km of this gk applied to my vector di. Okay, so even here I only am interested in the kth output, raw output. So this is going to be gk prime of this times the partial derivative beta km of this term here. Zi. Okay, and even in this, we know that beta km is going to occur only in one term. So this is going to be, so this is equal to gk prime of ti times, by the way, I have, yeah, the negative is already taken care. So I want to differentiate beta km. This is going to be beta k naught times z the 0th element here, plus so on, beta km. I don't need a vector here. Z mi plus so on, beta k cap m, z cap m I. Okay, so when you look at this, is just a summation, right? So when I differentiate this expression in the bracket with respect to beta km, you see that all the other terms become 0 because they are not dependent on beta km. So the only term that's going to have the beta km is this guy here, right? So this is going to then become gk prime ti times gm. Okay, that is all that we now have. So this is the partial derivative. Okay, so this is the final expression for the partial derivative of y hat ki with respect to beta km. Now this we plug into this equation here. So let me call this equation 1. Let me call this equation 2. So plugging in, okay, so I will maybe zoom out, and then you can verify for yourself if what I have done is accurate or not. Just take a minute. I'll just give you a minute to double check if my working is correct. So what we have done is the following. So we have first of all noticed that beta km is going to occur only in one of the k terms in the bracket here, that is here. So we only focused on that term, which is indexed by little k. So then what have we done? So now we have a square function. So then when we differentiate, say when we have y is equal to f of x whole square, and we want to differentiate this with respect to x. So we first say 2 times fx times f prime of x, right? That's all we have done. So we have a negative sign coming in because we have a negative here that's going to show here. Then we differentiated this term. So when we differentiated this term, it's going to be nothing but the softmax applied to this vector. So we are saying that the partial derivative is going to be the partial derivative of the softmax evaluated on this function or on this vector here times the partial derivative of the term that contains beta k, right? So that is going to be nothing but, so the inner product is going to be the sum of all of these individual terms. And in that inner product, only one term is going to have beta k. And that is going to be multiplying the output of the mth hidden layer. And so that is what we end up with here. Okay. So this is how we have computed the partial derivative of the loss with respect to a general km term, a general beta term that we have. Okay. So just make sure that there are no errors in what I have done. And if there are no errors, we'll proceed to the partial derivative of the loss with respect to alpha. And why do we need this? That you now clearly know, because we have the partial derivatives appear in the gradient term. And we are computing this for the MSC loss that we have used. So is it good? I hope there are no errors. I don't think there are, but double check, please. And please keep the big picture also in mind. The big picture is this. We want to find this quantity here, which is composed of partial derivatives of the loss with respect to each of the parameters that we have. It may look a little messy, but just for motivating our backprop, we have to do this. May I proceed?
Yes, sir.
Yes.
Okay, fine. So the next step in this, by the way, I hope that this is not a repetition for you, at least in this AIET series. I hope you're seeing this for the first time. If you've already seen it, I can go faster.
It's the first time.
Okay, fine. Then I will go slowly. And just like we identified what are all the output nodes that our beta km is going to have an influence on, now we will look at an arbitrary weight in the input to hidden layer connection. So now let's go back to our neural network picture. Now let's look at another node here. So let's look at, say, this node. So let's look at, say, this alpha MP. I hope you can see. Maybe I'll use a different color. Alpha MP. Is this clear? Is this visible?
Yes, sir.
Yes, sir.
Okay. So now my question to you is, alpha MP is going to impact how many of my output nodes? Meaning, which of the output node expressions is going to have alpha MP present in it? Please keep in mind that we have a fully connected network, meaning each of my input nodes is connected to each of my hidden nodes, and each of my hidden nodes is connected to each of my output nodes.
2 output nodes.
So alpha MP is going to appear where?
In ZM.
In ZM, but
And
we are
that-
interested in the influence of alpha MP in the output nodes.
Sir, if we are considering like the output node of YK and Y1, in both ZM is influencing us. So
Correct,
alpha.
exactly. So we have how many output nodes? We have capital K output nodes, right? And since we said that our network is fully connected, ZM is going to be connected to all of my output nodes. So with this, alpha MP is going to appear in how many of my output nodes?
All output nodes.
Exactly. So my alpha MP is going to appear in all of my output nodes. Okay. So that means that I will have to consider all of my output nodes in the gradient computation or in the partial derivative computation for alpha MP. Okay. In the beta case, we saw that beta km is only going to appear in the kth output node, right? So we effectively ignored the other elements of my output vector. But when we are computing the partial derivative of the loss with respect to alpha MP, I cannot ignore any of my output nodes. Okay, is that clear?
Yes, sir.
Yes.
Okay, So now let's go ahead and compute the partial derivative of the loss with respect to alpha MP. Okay, and this is important because we want to see why the term back propagation comes into picture. That's why we are doing this. It's a little messy, but please bear with me for the next 2-3 minutes, and then things will become clear to you. Okay, and to save you some time in terms of the computation, I will directly write the output and leave it as a small exercise for you to find the expression. Okay, so we now are writing out this expression. Right, so this is the weight that is going to multiply the pth input when it is connected to the mth hidden layer. That's what we are interested in. And this, we are finding the loss function, the partial derivative of the loss function with respect to alpha MP. In other words, what we are doing here is we are trying to understand the impact of a small change in alpha MP on the loss. Okay, just like standard definition of a derivative. In a derivative, what are we doing? We are trying to understand the impact of a change in the independent variable on the dependent variable. And that is captured through this expression here. That's all we are trying to do. Okay, so now when we are going to write out this expression, like I said, I'll write out the expression for you in the same fashion. So we are again going to apply the chain rule of the differentiation to find this expression. Okay, and similar expressions are going to come up in this term also. So just like we wrote out, we first apply the differentiation of the square with respect to alpha. So we have a 2 coming out, and then since we have a negative term here, the minus is also going to pop out. Then we are going to differentiate gk, this time with respect to alpha. Then the beta and the zm is going to remain, and the zm is where the alpha MP term is going to appear. Okay, so that is how the chain rule is going to be applied. Since we are running out of time for today, I will write out the expression and leave it as a small exercise for you to show it. Okay, so again we have 1 over nt. I'll write the minus sign here, I going from 1 to nt. And like we said earlier, we cannot ignore any of the k output nodes. So we are going to have something like this. Oops. K going from 1 to cap k. I have the negative term already outside, so I have twice. We have an expression that looks very similar. So I have yki minus yki hat times, everything is very similar. So I have a gk prime of ti times the partial derivative of this guy now. So this is where our alpha m is going to appear, right? So we have beta km times sigma prime. You know now where the sigma is coming from, right? The sigma is coming from our hidden layer. So we differentiate that. So we have this in a product, alpha m, and then we have our so alpha m is multiplying what? Alpha m multiplies what?
Input x.
Exactly. So we have the input. Okay. And then finally, alpha MP, right? So alpha MP is going to connect the pth element of my input to the mth hidden layer node. Okay, so it's very, very similar to what we have done. We are just only now considering where alpha MP appears. So alpha MP appears in the pth, it appears in Zm, and in Zm it's going to appear through the connection between the pth input layer node to the mth hidden layer. And so that's why we have the P coming in here. Okay, so this is what I would like for all of you to verify offline. Okay, now the last step in this is going to be to show how back propagation is going to play a role. Why it is called back propagation. Okay, now if you pay attention to what we have here, so my K goes from 1 to, my K goes from 1 to capital K. Okay, and if you look at this term, the entire expression that I have here, I can treat this as an error. Okay, so if you look at each of the terms here, I have yk y1i minus y1i hat, y2i minus y2i hat, and so on, right? So if I go back to my neural network, what I'm doing here is the following. So I'm computing, let me erase, let me just write this out like this. So I have yki minus yk hat I. Similarly, I have y1i minus y1 I hat, and all of these, right? So to this, I'm multiplying. If I go to this expression, I have a gk prime term there, and then I have another scalar. Now this is being summed over all of the k's that I have. So the way you can interpret that expression is as follows. So k goes from 1 to cap k, correct? And if I look at the beta terms that I have, let me erase this a little bit to make it clear. Let me erase this. So what I'm doing here is that I'm taking this error and back propagating it to the mth node. Okay, and when I do that back propagation, I have beta 1 m and all the way to beta capital K m. So I take the error at the output node and I back propagate that error to find the gradient of the loss at this particular node. Okay, I will repeat what I'm saying. So let me write that expression here just for ease of viewing. So here, what I just wrote in that in the third slide from here is the following. So I have minus 2 times yki minus yk hat I times beta km times some other terms. Okay, I'll just leave it as some other terms. And my k going from 1 to cap k, and my I going from 1 to nt, and then I have 1 over nt. So this is dou by dou alpha m p of L theta. So what I'm saying is, now this yk minus yk hat is like I'm finding the prediction at the output node. Then I am comparing the prediction with the ground truth for each of the predictions. And to find the gradient term with respect to the alpha MP, what I am doing is that I am taking this error and I am back propagating it. So let me use a different color so it's clear. So I'm computing the error at each of the output nodes. I am multiplying it with my beta, and I'm going backward when I am doing this. Okay, so I am back propagating my error from the output node towards the input node to find my gradient. Okay, so this back propagation is what is used to compute the gradient at each of the layers of my neural network. And it is called back propagation for this reason. So we compute the error at the output node and propagate it backward after appropriate weighting. So you see that this term has this beta km. So we weight the effective error with the weight that connects the mth hidden layer node to the first output node. Similarly, we weight the output, the error computed at the last node with the weight that connects the hidden layer, the mth hidden layer node to the last output layer node. So this is what is called back propagation. And please keep in mind that back propagation is used to find the gradient. Okay, it's an effective and fast way to find the gradient, elements of the gradient in our neural network. And so once this is found, once we have the gradient computed, we use it to update the weights themselves. Okay, so backprop is used to find the gradients, and they in turn are used to find the updates of our model. Okay, so this is the expression that is used to update the weights of our neural network. And the backprop is used to find the gradient term. And the reason for backprop itself, I hope, is clear from the graphical explanation that we just saw. Okay, I'll pause here and see if you have questions.
Sir, here you said we will multiply the error with beta.
Correct, correct, yes.
But then, sir, beta also we don't know, so we'll find it iteratively.
Yes, yes. So we do this iteratively. So you assume, you assume an initialization for your betas and alphas, and you continually update them. So those are nothing but what are here, right? So effectively, if to be precise, these are also vectors. You randomly initialize your weights, and then you carry out the gradient update.
Okay.
But the main idea for, or the main reason for why it is called backprop, I hope it is clear. We didn't derive this fully or thoroughly, but it follows from how we derived the previous expression. And the key is to note the nature of this term here. It's like we are computing the error. And to find the gradient, we are weighting each of the error terms with the betas. And when you put it on the neural network, it is like we are back propagating. So in the forward propagation, at each of the outputs, at each of the layer outputs, we are going in this direction, right? And in the back propagation, we start again. It's like we are almost flipping the input and the output. You can interpret it that way. And we weight it appropriately using the appropriate connections between the output nodes and the hidden nodes. I know it got a little messy, but the main idea, I hope it is clear. Okay, I'll hang around for a few minutes if you have questions. I know we are over time, but yeah, I'll wait if you have questions. And again, when we meet, maybe we can recap this once more before we go to the next topic. And in summary, what we have done is essentially, maybe I'll write out the summary here and I'll make use of this slide. So we defined a neuron. Then we looked at a multi-layer perceptron. Then we defined essentially the y hat for an MLP. Then we defined the loss. Then we came up with the gradient of the loss. Then we said how we can update our parameters. So this is in essence what we have done, starting from a basic neuron. And here we know what the IO relationship here is. This is summation of. So we built on top of this. And this essentially is found using backprop. Okay, so please keep in mind, backprop is used to find the gradients. And the update itself is happening through the standard iterative approach. Okay, and lastly, to wrap up our discussion, there are definitely challenges, like some of you just asked also. We don't know alphas and betas to begin with. That's a good point that you made. So how do we tackle this problem? Well, in most cases, you try to ensure that you randomly initialize your weights and also ensure that you ensure weights are not 0. Okay, and you randomly initialize typically. Now, another challenge when working with these neural nets is overfitting. So if you recall, we evaluated the number of parameters, right? So this actually grows with number of neurons, right? And we also saw how it grows, right? And so if we increase the number of nodes in our neural network, we run the risk of overfitting. And so that is again something that has to be carefully thought out, depending also on the number of data points that we have as to how we choose the number of neurons in our neural network. Now, another challenge when we are dealing with these neural networks is the input range. So if I am working with, say, images, so I could have images that are very bright, and I could have images that are very dark. So the range of input values that we have could affect how the model is the weights end up being learned. So we could have a large dynamic range. And another challenge that we spoke about is the network architecture itself, right? So I just mentioned to you that the choice of neurons is not, straightforward. It depends on a number of, parameters. So say number of data points, and then how the IO relationship is, which it's not very easy for us to estimate, right? And another challenge that we saw already is the issue with multiple minima in the loss surface. So what happens if you end up in one minima as opposed to another? So how do you measure the model performance? So you reinitialize number of times, you find minima for each case, and then maybe report like average performance or median performance. Okay, so these are some of the challenges that you will face when you are dealing with these neural nets. Okay, I'll stop here. And like I said, I'll wait for a few minutes if you have questions.
So can you share this slide with the annotations?
Yeah, definitely, I'll do that.
Also, sir, you said that you will point out to some references.
Yes, most certainly, I'll do that. Yes.
Okay, thank you.
Do we have any questions on the chat box? And you can feel free to also, share any questions that you may have subsequently also through the AIT team. I'll be happy to answer them. If there are no further questions, then maybe we can close this session. I'm sorry I went 15 minutes over. Yeah, I'll be around if you have questions. But yeah, feel free to log out if you have no questions.
Thank you, Professor. I think there were no questions from the participants.
Okay, yeah. Thank you all for your attention and participation. So we'll have the lab session tomorrow and we'll meet again in some time.
Thank you, sir.
Thank you, sir.
Thank you, Professor.
Okay, since there are no questions, I will also log out now. I hope that's okay, Talent Sprint team.
Yes, sir. Yes, Professor.
Okay, great. Thank you. Thanks for your support.
Thank you, Professor.
Thank you.